And I'm not going to try to make them all logically independent of each other. So this is not a class on quantum foundation, but to kind of give you a flavor of what are the fundamental assumptions that we have to make to formulate quantum theory. This is important because people are always trying to come up with a way, an alternative formulation of quantum mechanics. So, and some of the postulates are not very obvious why they should be the case, in contrast to what we see in classical physics. Okay, so the number one is that the physical state of a system is given by an L2 integrable function, called the wave function psi, which is a function of space and time. There is a more abstract formulation of quantum mechanics in which this postulate is replaced by the statement that the physical state of the system is given by a vector psi in Hilbert space, in something called a Hilbert space. A Hilbert space is essentially an infinite dimensional vector space with a positive definite norm. And in that vector space, there are the position operator and the position operators have position eigenvectors, which we write like this. So that means that if the position operator acts on the eigenvector x, so this is just a notation for a vector, it gives x as the eigenvalue. And so if I take this abstract vector in that Hilbert space and take its inner product in the sense of vectors with the Hermitian conjugate of this vector, then we get an object which is a function of x, the eigenvalue. And that is what we are calling here the wave function. And so in principle, this guy is just a function of time. So this is analogous to taking the projection of a vector along some basis. Okay, so anyway, that's not important. What's important is that the state of a quantum system is given by a wave function, and it's L2 integrable. That means that if I square it over all space, I get some finite real number n, which of course we can then replace psi by psi divided by square root of n. Then this new wave function, psi tilde, is normalized, right? So that was our postulate number one. Postulate number two is that the time evolution of psi is given by the Schrodinger equation. This is a real postulate. Well, all of them are, but there's no way that we can guess these postulates, but we can't derive them. So I(h bar), the time derivative of psi is minus h squared by 2n Laplacian del squared psi of x of t plus the potential energy times the wave function. This is the Schrodinger wave equation. And the Schrodinger wave equation is a linear equation. So it's a linear differential equation so that means that if psi1 and psi2 are solutions, so is the linear combination of psi1 and psi2, where C1 and C2 are complex constants. Okay, so this is an important this is important for the evolution of the system, right? Okay, so and from this it follows that if I have some system whose energy is given by p squared by 2m plus v, whose energy is given by E. So let E be the eigenvalue. Then, the wave function of that system is given by this particular linear combination. So these are the coefficient of linear combination analogous to C1 and C2. So this is, we use the Fourier analysis to express our wave function. Okay, so this was number 2. Number 3 was the Born interpretation. So what Born said was that, the probability of finding a particle, at or between, say, x and x plus, say, d of x is given by, we take the wave function and we square it. So this is a function of space and time, of course. Maybe we should write it in a slightly, in a different way. So psi xt squared d cubed of x. So this is the probability of finding the particle at x in a small volume around x. Okay, so this is the probability density. So, and a consequence of Schrodinger equation and this thing is the fact that the dynamics of probability density is given by the equation of continuity in the absence of a source or sink, that is, absence of a source which creates particle or something that absorbs particle. The probability density, which is given by psi star of psi, and the probability current density, which is given by h bar over m, imaginary part of psi star, gradient of psi, they satisfy this equation of continuity. Okay? And the consequence of this is that the normalization of the wave function, which is just given by this, it's a constant function of time. So once you fix the normalization of the wave function, it doesn't change with time. Okay, so I think this is basically covers what we covered last time, right? So that was a review.